This video is going to deal with electronegativity and polarity. And so you have a sense of electronegativity and polarity already from grade 11. Measure of an atom's tendency to attract electrons for the purposes of bonding using the Pauling scale, which you usually see in some tabular format or like this periodic table of electronegativities. So there's fluorine 3.98 here. I know it said 4.0 on the previous slide. Just need to realize the tables will give different numbers perhaps. I said 0.70 before, it's now 0.79. So the tables use different values. You just have to use the values appropriately. So there's a quick overview of what we did in grade 11. So we'll come back to that in a moment. But let's look at a fluorine-fluorine bond. So there's fluorine 3.98. We're going to look at a fluorine-sodium bond, and we're going to look at a fluorine-sulfur bond. So if we go back to our bonding, we'll see that a fluorine-fluorine bond with an electronegativity of 4 has a delta En of 0. Both atoms are the same electronegativity, so that's obviously nonpolar covalent. Electron sharing, equal sharing. Sodium and fluorine is different. Sodium has a very low electronegativity. That's the difference, far in excess of 1.7, so that's an ionic bond. We don't have to worry about those anymore. Sulfur fluorine, the difference is about 1.32, I believe, and so that's greater than 0.5, less than 1.7, so that's a polar covalent bond. And so we determine that because delta N is greater than 0.5. So now we can sort of interpret this notion of polarity or not in covalent bonds. So if the delta N is equal to 0, that's sometimes referred to as a pure covalent bond. It's like a neutral bond. There's an equal sharing of electrons. There is no charge separation. Each fluorine is pulling equally on the electrons. With the sulfur-fluorine bond, however, the delta N does not equal 0. It's greater than 0.5, so that we said that's a polar covalent bond. And a polar covalent bond is polar because there's charge separation. The fluorine pulls harder on the electron, so it has a negative aspect to it, delta negative. And sulfur, by extension, must be delta positive. You can also show that with vectors, the arrowhead pointing towards the more electronegative element. And so it's an unequal sharing of electrons. There's charge separation, so we basically have two charges associated with that bond, a positive and a negative. So how does this impact on molecules? Well, here's water, which has two polar bonds, and the orientation of those bonds means that the molecule looks like this. It's known as a bent or angular geometry. And what happens is because there's a positive and a negative aspect to each molecule, we get an electrostatic force of attraction that exists between these two molecules. The positive, negative, that's a force of attraction. And so that's known as an intermolecular force. And this force exists between molecules, hence intermolecular. And that force holds the molecules together. Water is a liquid at room temperature because of these forces of attraction between molecules. So that intermolecular force plays a vital role in the physical properties. Now, in terms of organic molecules, when we have a carbon-hydrogen bond or, which isn't shown, a carbon-carbon bond, both those bonds are non-polar covalent. So all hydrocarbons, alkanes, alkenes, alkynes, cyclics, benzene, for example, is an aromatic, would be non-polar because no polarity exists within the bonds. Halogenoalkanes, on the other hand, something like a carbon-iodine bond, that's nonpolar, as would a carbon-bromine bond. However, if it's a carbon-fluorine bond or a carbon-chlorine bond, there is a larger difference in electronegativity, and so those two halogenoalkanes would be polar covalent if they bond carbon to fluorine or chlorine. A carbon single bond O is also a polar covalent bond because the delta N is sufficiently large. And if you have a carbon single bond O or a carbon double bond O, you're going to have a polar molecule. An oxygen-hydrogen bond is also a polar bond, and so we see this in the hydroxyl functional group. NOH delta N is relatively large, and we already saw that in water, but it exists in anything with the hydroxyl group. So in terms of the nitrogen organic molecules, if we have an NH bond, it's a fairly small difference, but it's still polar. It's greater than 0.5, so that's a polar covalent bond between a nitrogen and a hydrogen. So you would have molecular polarity. However, that can change. And if you think about amines, and specifically a tertiary amine has 3 R groups attached to it, which would be 3 nitrogen carbon bonds, and no nitrogen hydrogen bond because they're all taken up by R groups. And if you notice, a carbon nitrogen bond is a nonpolar covalent bond, just on the very edge of nonpolarity. So we could consider amines then to be nonpolar molecules if they are tertiary. Primary and secondary amines, because they have an NH bond present, would be polar. And finally, if we consider amides have polarity, so they have a carbon-nitrogen bond, that is true, which is nonpolar, but amides also have a C double bond O, and we've already established that C double bond O is a polar covalent bond. So in summary, organic molecules, based on their functional group, will have polarity or not. So there's a list that explains it, and notice alkyl halides, amines can have both. And that's it for this video.